So we're going to talk a little bit here about strictly decreasing and strictly increasing. So it's important to realize that strictly increasing means one thing, a strictly increasing function, and we sort of compare that to just an increasing function, okay? And when we get to increasing functions, so they mean two different things, all right? A strictly increasing function talks about the y values. So obviously, if a function is increasing, you expect the y values to get bigger as you go along. A bit like my cubic here that's just been, drawn. So the graph, the y value gets bigger as you go along, so it's a strictly increasing function. If we reference an increasing function, that talks about the gradient has to be greater than 0, okay? So there'll be two terminologies that are very similar, or two statements. A strictly increasing or strictly decreasing, as opposed to an increasing or decreasing function. Here, we're talking about strictly increasing, which means we're talking about the y values. If the y value gets bigger as you work from left to right, we have an increasing function. Okay, so the fact that we have a 0 gradient is irrelevant. So the y values back here are negative, then they become positive, so it's an increasing function. If we have a look at this graph here in diagram 1, okay, it doesn't matter that we don't do the mod function anymore, but if we have a look at the graph here, you can see that in this case, the graph is not increasing at all. Okay, it's actually only increasing over a small section. It's decreasing in through here, it's getting lower, lower, lower. And then in here, it's increasing up to a point, maybe a bit further. And then you can see the y values are getting lower again. All right, and so that section in blue is the section where it's increasing. And so if we zoom that up, that's that section there. All right, so as it turns out, if we were to use technology, that's my turning point there at 1 on root 3. So it's only in that section there that the graph is actually strictly increasing. We can say the black section's strictly decreasing, but the blue section there is where it's strictly increasing. Obviously, the same thing applies for any sort of a graph. So if we're talking about decreasing functions, okay, decreasing, the y values are getting smaller. All right, so again, strictly decreasing, strictly increasing talks about the y values. So if we have a look here, consider what the y values are doing. I'll use that one. The y values are getting smaller and smaller and smaller as we go along. Okay, strictly decreasing function. As opposed to the cos function here, we'd have to pick a section where it's decreasing. So we could pick that section there, decreasing function, this section there, which is a decreasing function. And it's that second one here that I think corresponds to this part here. So the function is decreasing. It's really in reality from turning point to turning point, isn't it, in this case? So you can see there's the domain in which it's decreasing from. So that's pi there, and that's 0 there. All right, both points included because we're not worried about the gradients, we're just worried about the y values. Okay, so in other words, there's some little statements here. Let's see what they mean. If the derivative is greater than 0 for all the values in the interval, then the function is strictly increasing. All right. If the gradient is less than 0, then the function is strictly decreasing. Okay. Now, if we go to the x cubed graph, even though, all right, the graph of y equals x cubed is increasing the whole way, all right, but as it turns out, the derivative is 0 at a particular point, all right. So even though the derivative function, the gradient can be 0, it can still be an increasing function or a decreasing function. All right. So all this statement is saying, if the gradient is positive, it is definitely an increasing function, a strictly increasing function. But just because it is strictly increasing, it doesn't mean the gradient is positive. That's all that's really saying. All right. So if we have a good little example in here, state the subset of R for which the graph of f of x equaling x to the 4 minus x squared is strictly decreasing. All right. Quick graph sketch. If I take x squared out the front, I get x squared minus 1, I think, which is the same then as x squared, x minus 1, x plus 1. So a turning point at 0, because it's a repeated factor, 1, negative 1, and it's a positive quartic. So it's going to go down, up, turn, up. All right. Now, whereabouts is that function decreasing? So it's decreasing there until we get to that point. It's decreasing there from that point to that point. Yeah. So in reality, we need the turning points. All right. So what are the turning points? So we need f dashed of x equal to 0. F dashed of x is equal to 4x cubed minus 2x squared. Oops, 2x. So let's take 2x out the front. That gives me 2x squared minus 1. Solve that equal to 0. Therefore, we get at x equal to 0, I get x equal to 0, or I get x equals plus or minus 1 on root 2. So they're the x values, the derivative is 0. So it's come in here somewhere. Therefore, strictly decreasing over, well, what? So from minus infinity to that turning point there, which is at negative 1 on root 2, inclusive, union 0 to positive 1 on root 2, inclusive. Okay? I reckon that is about it. Right.